afternoon to all of you. First of all, I want to introduce myself. Myself Ankit Acharya, working as an assistant professor in Hasmukh Goswami College of Engineering. And today my content is GTU question paper solution of the subject of vector calculus and linear algebra of June 2014. So up to question number 3A, we already seen this question paper. So let's start with question number 3B. Here is a question number 3B. Find the basis for the subspace of P2 spanned by the vectors 1 plus x, x square, minus 2 plus 2x square, minus 3x. So there are 4 polynomials of P2, right? P2 means set of polynomial of 2 degree. We have to find the basis for the subspace of P2 spanned by these 4 vectors. Now generally we know that dimension of Pn, in general we know that dimension of Pn is equal to n plus 1. So in particular dimension of P2 is equal to 3. That means in any basis of P2 there are exactly 3 number of polynomials. Here we have 4 polynomials, right? 1 plus x, x square, minus 2 plus 2x square, minus 3x. So that means what? Among these 4 polynomials we want only 3 polynomials such that 3 polynomial become a basis of P2, right? So just randomly we are considering first 3 polynomials here. So we know that dimension of P2 is equal to 3, and for any basis of P2 contains only 3 vectors. So let V1 is equal to 1 plus x, V2 is equal to x square, and V3 is equal to minus 2 plus 2x square. Now we want to check that these 3 polynomials become a basis for P2 or not. And for that, what is the definition of basis for any vector space? First condition, it should be linearly independent, and second condition, the span of that set that is equal to vector space V. So here we want to prove that these 3 polynomials are basis vectors, and for that we want to check the determinant of this 3 polynomial. For this polynomial, if this determinant is not equal to 0, then these 3 polynomials are linearly independent, and if determinant is equal to 0, these 3 polynomials are linearly dependent. So let's see. The first row of this determinant is coming from the first vector 1 1 0. The second row is coming from the second polynomial. The coefficient of the constant term is 0. The coefficient of x is also 0, and the coefficient of x square is 1. So that's why the second row of this polynomial is 0 0 1. Now the third row is coming from this third polynomial. The constant term is minus 2. Now this 0 is because of the coefficient of x is 0, right? And the coefficient of x square is 2. So that's why this is minus 2 0 2 1 1 0 and 0 0 1, right? And minus 2 0 2. Now let's check the determinant, the value of this determinant. That is equal to 1, right? 1 into 0 into 2 minus 1 into 0, so that is 0. So 1 into 0 minus 1 into 0 into 2 minus 1 into minus 2, so that will become 2 plus 0 into 0 plus 2. So 0 into 2, that is equal to minus 2, not equal to 0. So that's why V1, V2 and V3 are linearly independent set of polynomials. Now there is one important theorem that if dimension of V is equal to n and you have n exactly n number of elements which are linearly independent of vectors V, then that vectors become a basis for a vector space V. So in that case, if you have exactly number of if you have exactly n number of linearly independent, where n is a dimension of V, where n is equal to dimension of V, and if you have exactly n number of linearly independent set of vectors, right? So in that case you don't need to prove that span of you don't need to prove that span of that basis elements that is equal to whole vector space V. So instead of we have to prove two conditions, right? The definition of basis is B is linearly independent and span of B is equal to vector space V. But if we have exactly n number of linearly independent vectors where n is a dimension of V, then we only need to prove that that set of vectors are linearly independent. Same situation happen here, that we know that dimension of P2 is equal to 3, right? And here we prove that these three polynomials of P2 are linearly independent. That means what? We don't need to prove that the span of these three polynomials that is equal to P2. That is automatically proved, right? So hence these three V1, V2 and V3 polynomials are basis vectors, basis polynomials for P2. Hence V1, V2 and V3 are linearly independent vectors of P2 and dimension of P2 is equal to 3. Hence V1, V2, V3 are basis vectors of P2. So this is a basis 1 plus x, x square, minus 2 plus 2x square. These three are basis vectors. Next question, question 3C. This question was asked in 4 marks in this question paper. Now express the matrix 5 1 minus 1 9 as a linear combination of 1 minus 1 0 3 1 1 0 2 2 2 minus 1 1. Okay, so here we want to express this 2 cross 2 matrix in a linear combination of this 3 2 cross 2 matrices, right? So let's check. So that means what? 5 1 minus 1 9, that is equal to A into 1 minus 1 0 3 plus B into 1 1 0 2 plus C into 2 2 minus 1 1. Now comparing with all coordinates, A plus B plus 2C is equal to 5, right? A into 1, you can see the first coordinate in right hand side, A into 1 plus B into 1 plus C into 2. So A plus B plus 2C is equal to 5. Now next is minus A plus B plus 2C is equal to 1. 0 into A plus 0 into B plus minus 1 into C, that is equal to minus 1, and 3A plus 2B plus C is equal to 9, right? Now we want to solve this 4 equations. You can see we have 3 variables, right? A, B and C, and total number of how many equations we have? 4 equations. So here we solve this 4 equations using augmented matrix, using matrix method. So here we are solving this 4 equations. You can see the first row, is coming from the first equation 1 1 2 5. So 1 1 2 5. The second row is coming from the second equation, that is minus 1 1 2 1, minus 1 1 2 1. The third row is coming from the third equation, that is the coefficient of ABC, that is 0 0 minus 1 minus 1, so this is 0 0 minus 1 minus 1, right. The fourth row is coming from the fourth equation, that is 3 2 1 9. So 3 2 1 9. Now first of all we have to convert this matrix, this augmented matrix, into row echelon form, or you can also convert it into reduced row echelon form. Now what is the meaning of row echelon form and reduced row echelon form, that you have to understand. There are some conditions to become a row echelon form matrix. The first condition is if there is any zero row. The first condition is if there is any zero row, it should be the bottom of the matrix, right. That is the first condition. Second condition is right, the first condition is if there is any zero row in matrix, it should be the bottom of the matrix. The second condition is if we have a leading entry, then below that leading entry in that particular column all the element should be 0, right. Below that particular column, below that leading entry in that particular column, all the elements should be 0. So now what is the meaning of leading entry, or sometime we call pivot, that is non-zero element. We are going from left to right, and the first non-zero element in any row, in that particular row, that is the leading entry of that row, and below that leading entry in that column all the elements should be 0. That is the next condition, second condition. And the third condition is whenever we are going from above to below, our leading entry is going from left to right, right. When in any matrix, whenever we are going from above to below, our leading entry is going from left to right. So that's why we have to convert this augmented matrix into a row echelon form. So the first row as it is, next processes are we are multiplying first row with 1 and add into the second row, and also we are multiplying first row with minus 3 and add into the fourth row. So R121 and R14 minus 3. So the first row is as it is 1 1 2 5. The second row is 0 2 4 and 6. The third row is 0 0 minus 1. The third row is as it is 0 0 minus 1 minus 1. Next is we are multiplying first row with minus 3 and add into the fourth row. So that's why the fourth row become 3 minus 3 0, then 2 minus 3 minus 1, then 1 minus 3 1 minus 6, that is minus 5, and 9 minus 15, that is 9 minus 15, that will become minus 6. Okay, now you can see in first row this one is our leading entry. Below that leading entry in that particular column we have now 0, right, all 0. There is no 0 row, so we don't need to convert that 0 row into the bottom of the matrix. The second row, in second row this is our leading entry, right. Below that leading entry we don't have any 0. So okay, one element is 0, but this is not 0, right. So we have to make that this element becomes 0. So what we have to do, we are multiplying second row with 1 by 2 and add into the fourth row. So that should be our next process, right. So R24 1 by 2, that means we are multiplying second row with 1 by 2 and add into the fourth row. So you can see the first matrix. Now first and second row are as it is, third row is also as it is, right. So 1 1 2 5 0 2 4 6 0 0 minus 1 minus 1. Here also you can see 1 1 2 5 0 2 4 6 0 0 minus 1 minus 1. Now the fourth row, when we multiplying second row with 1 by 2 and add into the fourth row, so the fourth row become 0. Then when we multiply 2 with 1 by 2, so that will become 1 minus 1 0, correct. So that is 0. then 4 into 1 by 2, that is 2, 2 minus 5, so that will become minus 3, correct. 2 minus 5 minus 3, then we multiplying 6 into 1 by 2, so 3, 3 minus 6, that is also minus 3. So the fourth row is now 0 0 minus 3 minus 3. You can see 0 0 minus 3 minus 3. The first, second and third row are as it is, right. Now next process, now you can see this is our leading entry. Below that leading entry we have all 0. In second row this is our leading entry. Below that leading entry we have 0. In third row this is our leading entry, right, minus 1. And below that leading entry, here below that leading entry we want 0 here, so that's why we are multiplying third row with minus 3 and add into the fourth row, right. So 0 0 minus 1 minus 1, right. When we multiplying third row with minus 3 and add into the fourth row, so the fourth row becomes 0 0 0 0, okay. So a plus b plus 2c is equal to 5. So the first row is a plus b plus 2c is equal to 5. The second row is 2b plus 4c is equal to 6. And from the third row we have minus c is equal to minus 1. So clearly c is equal to 1. When we put the value of c is equal to 1 in the second equation, we get 2b. You can see easily quite c is equal to 1, right. So put that value in the second equation, you will get 2b is equal to 6 minus 4, that is 2. So b is also 1, right. Now c is 1, b is also 1. So put that value in this first equation, you will get a plus 1 plus 2, right, that is equal to 5. That means a plus 3 is equal to 5. So a is equal to 2. So finally you will get a is equal to 2, b is equal to 1 and c is equal to 1. So c is 1, b is 1, a is equal to 2. So definitely we can express this matrix into a